Alrighty, we're going to go ahead and get started. My name is Sam Ricardo, and I'm a field application engineer at KEMET. I'm going to be the host for today's topic, which is So You Think You Understand Inductors. Today's presenter is going to be David Adeeb. And so with that, I'm going to go ahead and hand it off to David.
Thank you, Sam.
You're welcome.
Thank you everyone for joining us. Welcome to KEMET's webinar on inductor basics. And this webinar will walk you through the basics of inductor, and we'll keep it exactly at that. We'll just explain the basics of inductors. So without further ado, let's get started here. And my name is David Adeeb, as Sam introduced me, and I am a senior technical marketing engineer here in KEMET in Florida. And I have a degree in electrical and electronics engineering with a master's degree in business. I recently joined KEMET, so I'm fairly new to the team. And as far as my hobbies go, I like the outdoors and riding my bike. But anyway, so we'll talk today about today's agenda. The first thing we're going to do, we're going to define what an inductor is, and then we're going to explain a couple of features of inductors. One of them being inductance, and we'll talk a little bit about that in depth. And then we'll talk about factors that affect inductance, since it's such an important characteristic of inductors. And then we'll talk about the core, why we need to use a core and what a core actually does. And we're going to close with some terminology. We call it charging or discharging an inductor, and we'll explain what that means. And finally, we'll close with the characteristics of non-ideal inductor. So let's jump right into it. So what is an inductor? Well, an inductor is an insulated conductive wire that is wound, or meaning wrapped, around a core. And what an inductor does is that it stores energy in the form of magnetic field when you pass a current through the coil. And that current has to be a time varying current. And what time varying means, it means a current whose value changes with time. And when that happens, as you can see in this demonstration here, when a current passes through a coil of an inductor, you get a magnetic field or a magnetic flux that is generated within the core. In this case, we're not really showing this with a core, we're just showing it with vacuum or free space. But this is what happens when a current goes through the coil. You get an induced magnetic field within the core. And that induced magnetic field generates what we call an electromotive force. And that electromotive force is represented in this equation by the product of the inductance of the inductor times di dt. And di dt is the rate of change of current with respect to time. And this electromotive force is measured in volts. And as you can see and notice here, there is a little minus sign in front of this expression. And the reason there is a minus sign is that in terms of direction or polarity, the electromotive force is opposite in direction to the current. And what I mean by opposite is that it opposes the current that generated it in the first place. So in other words, to sum it all up, we can move on to this next slide here. So when a current goes through a coil, and that induces magnetic energy or magnetic field within the core, and that magnetic field generates the E, or electromotive force, that opposes the current that produced it in the first place. So by this explanation, we can basically say that the coil converts electric energy into magnetic energy and stores it. So by that it means here's the current, that's electric energy, goes through the coil, it converts it to a magnetic flux that is stored within the core for later conversion or later recovery, and we'll explain what that means further down the road. But before we move on, Let's just define some characteristics of an inductor. The first characteristic we're going to need to define is inductance. And inductance is probably the most important characteristic of an inductor. So what is inductance? Well, inductance is the inductor's ability or tendency to store that magnetic energy induced by or created by the flow of electric current. So as I mentioned earlier, a current goes through the coil and it converts it to magnetic energy. So how likely is this inductor to store that energy? This is what we measure by inductance. Another way to look at inductance is that it's simply the ratio between voltage and the rate of change of current with respect to time. And it is measured in henries. If you direct your attention here to this equation on the left, V equals L di dt. Well, V here is the voltage drop across the inductor, and di dt is the rate of change of current with respect to time. If I move this expression to the other side of the equation, I get the inductance equaling V divided by di dt. So it's basically the ratio of voltage to the change of current with respect to time. As some of you may already know, this is a differential equation that we can simply solve for I, and we get this nice expression here that tells us that I through an inductor equals 1 over L with times the integral of V dt, the integral of voltage with respect to time, plus I naught. And I naught here, or I prime, is the value of current at time equals 0. Now, on the right hand here of the slide, this graph actually shows you what happens to both current and voltage with respect to time within an inductor. So the red graph represents current. So with time, once this inductor is charged, is powered, is plugged in to a circuit, as time passes, current keeps increasing. It keeps ramping up and going up in value until it reaches a maximum value. But conversely, the voltage, the opposite happens with voltage. So voltage will actually keep dropping with time, as time goes by across the inductor. So current increases with time and voltage decreases with time. Another very important characteristic we have to define and well understand when it comes to inductors, it's really related to the core of the inductor. And this is what we call permeability. Some of you may be more familiar with terminology used when we talked about capacitors. And when it came to capacitors, we talked about permittivity. Permeability is the equivalent when it comes to talking about inductors. So permeability is of a magnetic core is the characteristic that gives the core the ability to concentrate or collect or keep or preserve the magnetic flux. So how likely or how good is this a given core is when it comes to storing and concentrating magnetic energy or magnetic flux? This is what we describe by the term permeability. Permeability of free space, as you can see here, it's a set value. It's a constant value of 4 pi times 10 to the power of -7. But when it comes to actual magnetic material or magnetic core, we introduced the term relative permeability, and this is represented by the letter mu r, and the relative permeability of a core is basically the permeability of that core to the permeability of free space. So as you can see here, and we'll talk about this equation in more depth in a minute, but knowing the permeability of the core helps us calculate the inductance of the inductor itself. So what factors affect my inductance? Well, the first factor we're going to represent here by the letter N is the number of turns of the coil. So how many turns do I have? That affects my inductance. The more turns I have, the more my inductance is going to be, or the better my inductance is going to be. The second factor we talked about kind of already is the core material itself. So when you have air or free space as your core, basically having no core, your permeability is 1. But when you have a magnetic core, like in this case, for example, soft iron core, your permeability is 600. So you actually get 600 more permeability but just by replacing air or free space with iron, iron core. And permeability is, as I mentioned earlier, represented by the letter mu. The third factor that affects inductance is the length of the coil itself. Not the core, but the length of the coil. So the longer my coil is, the more opposition I'm gonna have to flux formation. So the less basically my inductance is gonna be. And finally, my coil area. So the bigger or the wider my coil area is, the more inductance I'm gonna have. So area here is represented by the blue letter A, and I forgot to mention that coil length is actually represented by the green letter L. Putting all of these variables together, we get this nice equation. L, which is inductance, equals the relative permeability of the core times the permeability of free space times n squared, and n is the number of turns as I mentioned, times my area, A, divided by the length of my coil. Now, keep in mind, there's a little bit of a trade-off here. It is easy to say, oh, the more turns I'm gonna have, the higher my inductance is gonna be. Well, the more turns you're gonna have, the longer your coil is gonna be, and thus you might actually end up reducing your overall inductance. So you have to be careful with that trade-off factor a little bit. So we talked a little bit about a core and permeability of a core, but why do we even need to use a core? Well, a core does 3 things that are very important to understand. First of all, from a functional standpoint, a magnetic core stores that recoverable magnetic energy, as we explained earlier. A coil converts electric energy to magnetic energy, and where does that magnetic energy get stored? It gets stored in the core. So the better my core is at storing that energy, the better my overall inductor is going to be. Now, secondly, from a mechanical standpoint, a core helps give strength and stability to my inductor. So it helps provide support for the windings themselves, as you can see here in this little picture. Now, finally, from a magnetic standpoint, a core provides the medium that, to concentrate that magnetic flux so none of it escapes to the surrounding environment. So from a magnetic standpoint, it concentrates and it helps preserve that magnetic energy within the inductor without it escaping. Now, we're not really gonna go into the different types of cores in this webinar. As I mentioned earlier, we're just gonna keep it to basics, but let me just briefly mention that there are 3 different types of cores. Air or free space, which means that you're basically not using any core. And number 2 is ferrite or iron core. Number 3 is metal composite. And they each have their cons and pros. And if you want to find out more about that, join us this Wednesday in our webinar. We'll talk more about cores and the different types of cores and what they each do. Now we talked about inductor and we defined inductance and all of this, the factors that affect it and all of that. So now we have a good understanding of the basics. But how does an inductor actually behave when we plug an inductor as part or an element of an electric circuit? Well, you can think of it like there are 2 modes of operation when it comes to inductor. There is the inductor charging and the inductor discharging. And let me explain what I mean by that, because they're really not technically correct terms to use, but we kind of borrow them from our capacitor terminology. So by charging an inductor, what I mean is when an inductor is part of a circuit and there is increasing current going through it, you will get this voltage drop across the inductor with the positive up on the top and the minus at the bottom. So the current obviously flows in this direction, and the inductor is set to be charging. And what we actually mean by charging is that the inductor is acting as a load, meaning that it's drawing electric energy from the circuit and converting it, as we explain, to magnetic energy and storing that magnetic energy in its core. So all we're really doing at this point, we're just converting electric energy to magnetic energy and building up that energy within the core. That's all the inductor is doing, just drawing energy and convert it to magnetic energy. And you can see that on this blue side of the graph with the value of current through the inductor going up with time until it reaches a maximum value. Now, once it reaches a maximum value, the voltage drop here across the inductor will become 0, and the inductor acts virtually as a short. Okay, so what is the second mode of operation? Well, it's called discharging. And again, we're borrowing those terms from the capacitor terminology. So what does discharging an inductor mean? Well, it means that there is decreasing current going through the inductor. And as you can see here, the polarity of the voltage drop across the inductor has reversed. So there is decreasing current going through it, and now the inductor is no longer acting as a load, but as a source. And what I mean by that is that now it's taking that magnetic energy that's been stored in the core and converting it back to electric energy and sending that electric energy back to the circuit that it got it from in the first place. And you can see that here in the green part of the graph, where the value of current keeps decreasing with time, and it will eventually reach 0 when the inductor is completely drained out of its magnetic energy and it has converted everything back to electric energy back into the circuit. So some of you that may be familiar with capacitors, you all know that there is no such a thing as an ideal capacitor. It just simply doesn't exist. I mean, for that matter, there is no such a thing as ideal anything. Well, inductors aren't any different. So an ideal inductor does not exist. All the inductors that we work with are non-ideal inductors. And non-ideal inductors can really be represented by an inductor L, which in this case is, just that this is the ideal portion of the inductor, connected in series to a resistor named R. And what we mean by R is really our DC resistance, or DCR. And this is basically just the resistance of the copper material that is used within an inductor. So it's just the inherent resistivity of the material to electric current. But keep in mind that this R is actually a very important factor, because the higher your R is, the higher your DCR is, the more heat you're gonna get dissipated within the inductor, and subsequently the more your power loss is going to be, because power loss is I squared times R. So the higher R is, the more power you're going to lose through the inductor. And having said that, now the less efficient your inductor is going to be. So your efficiency drops as your R resistance or DCR increases. Now, and we're not really gonna go so much into detail in this slide here, but before we close our discussion of inductors, we kind of need to define a very important factor or term that you will kind of hear a lot, which is self-resonance frequency. Simply put, self-resonance frequency is the frequency after which an inductor starts behaving as a capacitor. So if you direct your attention here to this graph, this is impedance, and as frequency keeps going up, the inductor's impedance increases. It's directly proportional to frequency until it reaches a certain value, and that value differs from one inductor to the other. After that value, if frequency keeps going up, Now the inductor is gonna start behaving as a capacitor, and it's no longer going to exhibit the characteristics of an inductor. And you kind of see that here on the left, where before self-resonance, most of the current is going to be going through the coil or the inductor piece of the circuit. But after self-resonance, most of the current is going to be going through the capacitive part of the circuit. And please do not understand or do not think that there is going to be physically a capacitor connected to the inductor. This is just a demonstration to, basically to demonstrate the virtual characteristics of an inductor. So the point to take home here from this slide is that self-resonance is the point after which an inductor becomes like a capacitor, okay? Now, the last thing we're gonna cover for today's session is the loss, the different types of losses that we see or experience within an inductor. One of them is the resistance, R, which we already kind of talked about, which is the copper loss or resistive loss. And this is basically just a loss in energy that you get as a result of the inherent resistivity of the material that the inductor is made out of, or the coil is made out of, okay? Now, the same way there is no such a thing as an ideal inductor or a resistor, there is no such a thing as an ideal core, okay? And, with cores, we talked about the coil converting the electric energy into magnetic energy and storing it within the core. Well, since the core is not ideal, you're also gonna get some loss in that magnetic energy from the core itself. And this is what we call core loss. So not all the energy that you're going to, not all the magnetic energy that you're going to store in the core are you gonna be able to later convert it back to electric energy. Some of it is gonna be lost as part of the non-ideal characteristic of that core. And this is what we call a core loss. And finally, fringing loss. Well, fringing loss, you can really think of it like you can see here in the picture. If this is the core and I got magnetic energy stored in this core, some of this magnetic energy is gonna come off to the side. It's gonna leak or fringe out. That's why we call it fringing loss. It's gonna fringe out to the surrounding medium and I'm gonna lose some of this magnetic energy. And this is what we call a magnetic loss just by virtue of the magnetic flux escaping the core material itself to the surrounding medium. So let's recap. What have we learned so far? Well, we've learned the definition of an inductor. So we defined an inductor as an insulated conductive wire wound or wrapped around a core. And I should stress that the word insulated. The coil must be insulated, and if it's not insulated, you're not going to have an inductor anymore. You're just going to have a short, a shorted wire, basically. And one of the, I should take the opportunity to mention that one of the most common modes of failure when it comes to inductors is that you lose insulation between the different turns. So in the event, usually we see it very common that too much current is passed through the coil, and the coil heats up so much and it melts that insulation, and then you get a short between two or more turns. And if that happens, you no longer have an inductor. It just doesn't function as an inductor anymore. And we also define the characteristics related to inductors, namely the inductance and permeability. And we talked about core permeability. And we talked about inductance and how it's the tendency to store magnetic energy. And we also talked about factors that affect inductance, which are the area, the length of the coil, the number of turns, and the nature or the type of core that we use, whether it's air or an actual magnetic core. And we finally closed with charging and discharging modes of inductor within a circuit, and finally the characteristics of non-ideal inductor. And with that said, I'll turn it over back to you, Sam.
Thank you, David. Wonderful presentation, very good information. Before we open it up to the Q&A, if you do have Q&A questions, please type them into the Q&A box. I just wanted to go over a few things. After this presentation's over, if you do have questions, please feel free to submit the questions to the link that will be on the last slide of the presentation once you receive it. Also, please join us for our upcoming webinars. We have one this Wednesday, Construction and Characteristics of Power Inductors, and that's going to be at 9 a.m. Eastern and also 11 a.m. Eastern, same time as right now. And then the following Monday, Explaining Losses in Magnetics-Based Components. That's going to be at 9 a.m. and 11 a.m. Eastern again. So with that, we'll open them up to questions. So David, the first question is what type of cores does KEMET offer?
Well, we kind of mentioned that a little bit briefly here. Ferrite iron cores and metal composite. Those are the types of cores that I'm familiar with. I'm not sure if we offer other types of cores as well. Maybe you know, Sam, but as I mentioned on Wednesday, we'll get much deeper into cores and different types of cores.
Yeah, that's actually correct. We offer ferrite and metal composite. The ferrite is going to be our through hole, and we do have one ferrite TPI inductor, surface mountable. And then our metal composite inductors are going to be all surface mountable. Our next question is influence of air gap on inductance. So how does air gap influence inductance?
Yeah, so this is kind of shown here. I kind of skipped over it a little bit because it's kind of outside the scope, I guess, of this webinar. But I mean, we do offer, or some a lot of other manufacturers also offer, cores with like a little air gap to kind of, enhance that behavior. But not sure if you perhaps have any other insight to add to that, Sam.
I think that, and then I think you actually touched on one of the slides. It was the one with the turns, the windings. Basically, yeah, that one. The number of, well, the turns and how, and I guess it's coil. Well, so I guess the air gap is going to come in. Well, I guess you touched on most of it, but yeah, the air gap is going to have a slight influence on it, and we could provide more information on that from our team as well. Yeah, I'll take a note to get that answer for you. The next question is, will you speak about the itinerary on the next webinar? So I don't have much information on that webinar. David, do you have much on it? My guess is that they're just going to be talking about the design and characteristics of power inductors. So that's going to probably be mostly targeted towards metal composite inductors with a little bit of target on the ferrite inductors.
Oh, okay.
Do you have anything to add?
Yeah, I mean, actually, you will find a full description of the webinar itself on our engineering center. And that is basically ec.kemet.com. If you would like me to, I can maybe type it in here somewhere. Let's see if I can type it here. Okay, not, yeah. I don't know if you have, I don't see the chat window, Sam, but if you see it at your, oh, here it is, okay. So ec.kemet.com. So I send that through chat. This is our engineering center resource website, where you'll actually find not just the description of this this webinar coming up, but you will see a full calendar of our events, webinars that are coming up with times and dates. And for each webinar, you will actually see a short description of the webinar and what the webinar tends to intends to discuss. So you will find more information there in our engineering center.
Perfect. So it's now 11:30, which is supposed to be our close time. David, did you want to try and answer a few more questions, or should we go ahead and answer them all after the training is over?
Maybe we'll take one more and then we'll finish up with that.
Perfect. So the next question is, what are the critical parameters when picking an inductor?
Okay, the critical parameters. I mean, obviously, inductance is the most critical of all. This is why we kind of spend quite a bit of time covering inductance and what it does, because inductance determines how well your inductor is going to function. Yeah, I think we talked about it here. And then obviously the type of core. As you already mentioned, Sam, you know, the different types of core, whether ferrite or metal composite, affect the inductor quite a bit. So those are typically the two more important factors that people consider when selecting an inductor.
Yep, and just to add on that, I think a few of the main parameters that you would need to consider, number one is going to be the inductance, and I think that's pretty obvious why. You're also going to need to look into the chip size or the dimensions of the part to make sure it's going to fit into whatever your application is. Another important thing is the temperature range. A lot of inductors are rated to roughly around 105 degrees C. Some of them, such as our MPX inductor, could get up to 155 degrees C. I think it's very important to know where that's at, because that temperature range is going to have influences on other parts of the device, such as the current, and that brings me to the next part. The current rating of the part, and that's the RMS current and saturation current, are very important, as well as the DCR, which David covered earlier, and as well as the self-resonant frequency. So I think all of those parameters are very important when picking or deciding what inductor you're going to use. And then, of course, we do the hard part for you of deciding what type of inductor, what core material you would want to use based off of all of those different parameters.
And in the chat window, just to add to that, Sam, I also sent to all the participants the link to our KESIM tool, KESIM 3.0. That's our new KESIM tool. And the reason I did that is because in that KESIM tool, you will actually be able to select any of KEMET's inductors, the product offering we have for inductors with different parameters. And the tool will actually give you a graphical representation of the power loss within the inductor, the temperature rise, and inductance. Okay, so you know, take a look at that tool, because it will you know, model for you and simulate basically how a particular inductor within the KEMET's portfolio behaves within a circuit, you know, in terms of power loss, temperature, power loss, inductance, and temperature rise. So take a look at there. You might find some useful information, and you can also download the spec sheet, and you find a lot of technical information on our inductors as well, if there is a particular one that you're wondering about.
Perfect. Thank you, David. So with that, please note that if we have questions that haven't been answered, and I have a list of them, we will be reaching out to you in the next day or so with the answers. So please look for that. And if you have questions in the future, please feel free to use the link on the last page of this presentation to submit a question, and someone from our team will answer it as quickly as possible. With that, wish everyone a great rest of your days, and take care and stay safe.
Thank you, Sam. I appreciate it. Thank you, everyone, for joining us, and we'll see you next time.
Thank you, everyone.
Thanks. Bye-bye.